Okay. Good afternoon, everyone. So welcome to lecture 5, EC 5882-6882. So before I start, I just mentioned few things. The first one is that your assignment 1 is on. So I believe you already know that. And please read through that, answer the questions, and upload your results. This is an individual assignment, so everybody should submit one file. Okay? The questions are very easy, similar to exams. Okay? It's not. Yes, it is. Okay.
Provide us with a consultation hour on Monday around from 10 to 1 within this one. Is this possible?
Consultation on Monday.
Because on Tuesdays we have lab, so by the time I arrive there, it's already halfway through.
So on Tuesday, actually, your lab starts from 6, I think.
But I have other lectures. So.
Okay. Actually, we don't have that much option because we don't have that much empty room in the department at this time of the year. So actually, the time that I allocated for the consultation hours is the time that we have help desk running at that lab. All right? And from this week, actually, the help desk that I'm on Tuesday, I'm on the help desk from 5 to 10. So 5 o'clock to 10 p.m. So it's 5 hours of help desk. I'm there. If you have questions, you can come at that time. I think that
Any time from 5 to 10?
any time from 5 to 10, you can come on Tuesday. But on Thursday, only 5 to 6. Okay? Yeah. So the consultation hours is originally from 5 to 6 on Tuesday and Thursday. But from 5 to 6 and then from 6 to 10, I'm running help desk in the same location. So you can come from 5 to 10, from week 6. I mean from next week. Okay? Okay, so and for those who just arrived, so the assignment 1 is on. So please try to answer those and submit by time, which is end of next week. So before I'm going to lecture 5, I'll give you a very short review on lecture 4, what we introduced there, because what I'm going to deliver today is a little bit dependent on the materials that we covered last week. So last week we introduced transmission lines. So I introduced transmission line. And we defined different types of transmission lines, which was the two-wire lines, coaxial cables, and strip lines or microstrip line. Okay? And then we mentioned that the equations that the transmission lines are following is the telegrapher's equations or telegraphist equations. And based on those, we found that the voltage and current on a transmission lines are followed by these two equations. And then we said that V plus and I plus related to the forward traveling wave, and V minus and I minus are backward traveling waves. Okay? And then we define the intrinsic impedance or characteristic impedance of a transmission line as Z naught. And then we said that this Z naught equals to V plus divided by I plus, or it is V minus divided by I. Yes. And this is minus actually. And we said that if a transmission line is a combination of an R and L and C and G, so if we define a transmission line as an infinite number of these blocks, which I mentioned before, and this is the R, this is the L, this is the C, and this is the G, then we can define this characteristic impedance as R plus J omega L divided by G plus J omega C. Okay, and omega is the operating frequency. Also here we say that this gamma, so this gamma equals to again R plus J omega L multiplied by G plus J omega C. And then if a transmission line is lossless, then we say that the gamma, which is alpha plus J beta, so this is the attenuation constant. Gamma is the propagation constant. Yeah. So gamma is the propagation here. So you see that with gamma, the wave is propagating through the direction of Z. Yeah. And then beta is the phase constant. Okay. And then for a lossless line, we say that for a lossless line, we say that alpha equals to 0, so there is no attenuation on the transmission line, and then we can write down that the gamma is equal only just J beta, then beta actually equals to square root of LC, and then the Z naught equals to square root of L over C. Okay. And then And then we said that if we have a transmission line connected to a load of ZL, and we say that this point is, for example, equal to Z equal to 0, and then this point is Z equal to D, and this is a transmission line with the characteristic impedance of Z naught, then we can define the input impedance of this segment of transmission line terminated with ZL equals to Z naught ZL plus J, I think Z naught tan of beta L, and then Z naught plus J ZL tan of beta. And we can define the reflection coefficient at this point as gamma naught or gamma L. So gamma L equals to gamma naught equals to ZL minus Z naught divided by ZL plus Z naught. And this is the reflection coefficient at the load. And if we want to find the reflection coefficient at any point on this transmission line, then we said that from here we said that this gamma of D, for example, at point D equals to gamma naught e to the power minus J 2 beta D. So,
so in the upper
yeah.
equation beta D, right? Tan beta L, tan beta D, L is D.
Yes, here L is D. Thank you. And L equals to D. At any point D, then we can see that the input impedance coming from this point, this equation, and then the reflection coefficient is coming from this equation. Okay? And then we had quarter wavelength transformer. So the quarter wavelengths transformer. I mean that this length, if it is equals to quarter of a wavelength, is lambda 4. Then we said that the Z in equals to Z naught squared divided by ZL. Okay? And we used it to transform an impedance of ZL to Z in by just defining the value of the Z naught. All right? And then we derived equations for the matching conditions of a transmission line terminated by an load and is connected to a source which has another impedance of ZS. Okay? And we said that if we look at the impedance of this transmission line connected to the load and assume that the length of this line is, for example, L, and the input impedance at this point is Zin, then the perfect power transfer from your Vs to ZL happens if your Zs is Zin conjugate. So this is what we found. And then the maximum power transfer, PAV of max equals to one over 8 Vs squared divided by Z naught. So this is the maximum power that we can
What the source impedance to be
to
the
the load.
Z is to be the conjugate of Z in it is for perfect power transition.
Yes.
What do you mean by perfect power transition?
I mean the maximum power that we can transmit. So the formula that we had here is like this, that the power that we can deliver to the source equals to 1 over 8 Vs squared divided by Z naught multiplied by 1 minus gamma S squared 1 minus gamma S gamma in squared and 1 minus gamma in squared. So you see that the maximum power will transfer when this gamma in and gamma S equals to 0. So we will use this today, that how we can try to match, for example, a load or a load connected to a transmission line to a source that has a different impedance, how we can do this. So this is what we covered last week. Okay? Any question on this?
Gamma S represents the reflection.
Gamma S is reflection coefficient at the input. So gamma S equals to Zs minus Z naught divided by Zs plus Z naught. And gamma in, exactly, you can substitute Zs with Z in. Just pass this through your friends. Thank you. Pass this to your friends. Okay, so any question on the previous lecture? So guys, I encourage you to study more during your private time. If you have questions, please come to the consultation sessions, ask your questions, look at the questions. Please do not think that the questions that we are solving in the class or we are providing you during the lecture or exercises that we have in the lecture are sufficient. So please go through your books, questions. If you have any question about those, please come and ask. So this is a master unit. Actually, we suppose that you yourself are already mature to solve questions by yourself. And because of that, we don't have any tutorial class or, I don't know, additional sessions for this. All right? And, okay, this lecture is about the Smith chart and impedance matching. So a Smith chart is what you have in your hand. And then we are trying to use this Smith chart as a very useful tool to do the impedance matching for the RF electronic circuits. Impedance matching and maximum power transfer is one of the most important topics because you define for example, we have a network 1 and then we have a network 2 and then we have a network 3. So I want to connect these 3 together. Okay? Are you with me? We want to connect these 3 together. But the purpose is that if I have a source here and I call it Vs, and I want at the end connect this to a load here at this point, can I connect these directly and then ensure that the power that I'm generating here is exactly the maximum power is delivering to this load or not? Yes. I'll tell you today. So we are talking about this network today. Network, you can assume that single component, a transistor and its biasing, all is network. But I will tell you that what's the meaning of network. It's a good question because network in different area of engineering is different. But in electrical engineering network, actually, you define a circuit by its inputs and outputs and the ports. Okay, we will reach to the network today. So to make sure that the maximum power is transmitting from the network 2 to network 1 and then from network 1 to network 3, that we put a matching circuit between these. So matching network. And then in such a way that this equation or this condition is satisfied. Okay? All right, a Smith chart. So this is what I just tell you, that we can calculate the gamma of a transmission line terminated with a load ZL. At the point ZL, we can calculate the gamma from this equation. And then I can understand from this equation that if ZL or Z0 is complex, then the gamma is complex, is a complex number. And then we can define this gamma with the real part of the gamma and the imaginary part of the gamma. Or I can write the gamma is in a polar format. So the amplitude of gamma and then the theta, phase of that. Yeah. And then the phase is coming from this equation. All right? And the amplitude, you know that the amplitude also equals from square root of gamma r squared plus gamma I squared. Okay? So if I draw this gamma on a polar format, I mean on this circuit that you can see, then at the center I can say that the absolute value of the gamma is 0, and then in radius 1, the absolute value of gamma is 1. So any value of gamma, I can represent it or I can transfer it into this plane. So this is a gamma plane representation of this gamma naught. Okay? So based on the impedances that we tried last week, so assume that your input impedance is ZL, and then based on this ZL, and then the value is 0. I mean it's short circuit. And then we find that the gamma equals to -1. So here is the short circuit on a polar format. So the amplitude is 1 and the phase is 180 degrees. Are you following me? Is it clear? Okay. And then, for example, for the impedance of infinity or open circuit, again the gamma we can calculate as a 1. So again the amplitude is 1 and the phase is 0. Or for a match. So for a match we know that the absolute value of the gamma is 0. So it is at the center. Or for any other value, any impedance that we have, any impedance that we have in the world, then there is a point exactly representing the value of the gamma for this impedance in this circuit. So if I normalize the impedance and then change it to the reflection coefficient, I mean I can write down that gamma naught equals to normalized value of ZL divided by Z naught minus 1 ZL divided by Z plus 1. Then any Z has a representation here. So this is what we learned last week. Okay, then what did Mr. Smith do? Mr. Smith said that, okay, if we have this representation of the gamma, and now if I want to find if I pick a point here, any point here, and I want to find the Z, the equal Z of this, then how I can manage this easily on graphical format, okay? Assume that we know the gamma, and now we want to find the Z, all right? So he has written this formula that if I know the gamma, then the gamma D, or the gamma at the distance of D from the load, is coming from this formula that I already mentioned here. So gamma D is coming from here. Okay?
This D is actually the distance from the load.
Yes. So the gamma naught is the reflection coefficient of the load, exactly at the port of the load. And then if we moved on a transmission line by the length of D, then we say that at this point it's gamma D. Okay? Then the input impedance that we defined, and then if we normalize it based on the characteristic impedance of your transmission line, and we denote it by the lower case as Zin of lower case, is again coming from this R. It has a real and imaginary part, and coming from this formula. Okay? Is it clear up to you? So just follow me in this, the beginning steps, then it will be very easy to understand this. It's not as difficult as that horrible shape. Okay? So you are happy with this? All right. If you are happy, then I just replace this gamma D with its real and imaginary parts, which I told you here, that each gamma has a real and imaginary. Now, if I want to find this Z in, if I know this gamma R and this gamma I, then I need to find this R and X based on this gamma R or gamma R. So I rearrange this formula, and then equals the real part and imaginary part. And then I understand that the R is coming from this formula and X is coming from this formula. R plus Jx equals to this. I try to just equalize the real part and imaginary part. Clear? Then based on these two equations that I have, I can write down the equations. I mean, I can write down this equation or this equation in such a way that the first equation is just dependent on R and the second equation is just dependent on X. Okay, I have two equations. One of them is only dependent on R and the other one is dependent on X. So what we want to do, again, I go back. We have gamma and I want to find the Z in. Other way is very easy. Gamma equals to Z in minus Z naught divided by Z in plus Z naught. It's easy. But the other way, if we have gamma and want to find that, so I said that this Z in has a R and X, and this gamma has a gamma R and gamma I. I can write this equation and this equation. And you can see that these two equations are a kind of equations for the circles. And these circles, for example, this circle has a center of R divided by R plus 1 and 0. And this circle has a center of 1 and 1 over X. This circle has a radius of 1 over R plus 1. And this circle has a radius of 1 over X. Then on this graph, if I draw these circles, then I can say that, for example, if I draw one circle, I know that based on different values of R, then I know that the value of R on that circle is constant, always constant. Or if I draw these circles, the second type, then I can understand that any value on this circle has a constant value of X. Okay? So this is what Mr. Smith did. So he defined these two types of circles on this graph, on this base, on a gamma plane base, and then said that, okay, if I want to find a value of R equal to 1 and, for example, X equal to 1, which is representation of the Z in, actually, small z in equals to 1 plus J1, then I have to find the intersection of the circles R equal to 1 and X equal to 1. This is how this shape works. So this diagram has two types of circles, R constant and X constant. And then if you want to find any Z in normalized impedance in this plane, then it's just you need to find the intersection of those 2 points, those 2 circles. Okay? Easy. So the first equation is going into this type of graph. So it has a center somewhere on the gamma I equal to 0 line. So here you see that one of the centers is in the center, it has one coordinate of 0. Okay? So the center is on this, and then based on the value of R, we have different circles. So if I am looking on an impedance that has a R of 50 ohm, then R equals to 1 if I normalize it to 50. Because Z in, I said that Z in equals to Z in divided by Z net. So if I'm looking for a impedance that the real part of the Z in is 50 ohm, then it is somewhere on this circle. Okay? If I'm looking on an impedance that its real part is 150 ohm, then it is in this circle, somewhere on this circle. All right? And then for the imaginary part, which is the second one, then we are going into this graph. So these are the circles, and you see that the center, one of the centers is 1, and then the other one is 1 over x, and then the radius is also 1 over x. And these are these circles, but just part of it is inside the Smith chart, and part of it is out. So, and we are always interested in inside this one, because gamma is between, gamma, absolute value of gamma is always less than 1. It cannot go out of 1. All right? Again, if I'm looking for a impedance that the imaginary part equals to 1, then it is somewhere on this circle. Or imaginary part equals to 3, actually 3z naught. 100, j 150. It's here. If it is j minus j 150, it is on this circle. And I just want to tell you that we don't have negative r, because resistance cannot be, never ever can be negative. Okay, we always have positive. But imaginary part could be positive or negative. Okay, and then if I'm looking for a 1 plus j1, then I should find the intersection of this circle and this circle, which is, for example, somewhere here. So here, if you have a combination of these two together on one chart, so these circles are the constant r, and these circles are the constant x. And then you can find easily any value on this. So we use this technique for transformation of impedances, for moving impedance on a transmission line, and for combination of different levels of impedances together, cascading of impedances together. Okay. So based on this equation here, we see that if I have any gamma, for example, I assume that I found my gamma at this point, okay? And then I want to find the gamma at this point, find the gamma. At this point, I just need to turn around by 2 beta d. Are you agree with me or not? Sorry? Towards generator, because generator is here and load is here. Okay? So if we have the gamma and we want to find the gamma at the end of this transmission line, which is the length is d, then we need to just rotate. We need to change the phase of this value only by 2 beta d. And beta d is the electrical length of the circuit, and it's different for different frequencies. Okay? Clear? No? No. Assume that this point is gamma naught. Okay? So this point, or we have here, assume that this point is gamma naught. Okay? And this gamma naught has an amplitude and a phase. So I want to move through this transmission line and find the new gamma at this point. And I know from this formula that if I want to find the gamma at point D, I just need to put the original gamma and then change the phase by 2 beta d. So I need to change the phase of this point by 2 beta d. So I find, for example, what is the phase of this? It is 34 degrees, and then the 2 beta d I calculate. So I know the length of the transmission line is 5 centimeters, and the beta is 2 pi over lambda, and lambda at this frequency, for example, is 1 millimeter, and then I found the 2 beta d. And then by that amount I change and come here. All right? And then I know that the amplitude is the same as before and the phase is just changing.
Why are we going like clockwise? Why don't we go
Okay.
anti-clockwise?
Because it is mentioned there on your Smith chart that if you look at your Smith chart, can I have one of those if there is any extra? If there is any extra, you don't have. Maybe at the back. So if you look at the Smith chart, you see that in the outer part of the circle, in the outer part of the graph, we have two sets of numbers.
It says weighting towards generator and is given an arrow clockwise.
Yep. Yep. Is
The point of relation when we located is set in at the that the equal to hour when we move along the constant gamma.
I'll answer your question. Okay. So if you look at this section, which is mentioned wavelengths toward generator. I mean that if you want to move towards the generator, which we want to do, so we have the ZL, and then we want to see that what is the input impedance or what is the gamma when we move towards our source. So then you have to rotate by this way. So this is towards generator. And then if you look at this point, you see that it says that towards load. So if we have the generator, I mean if we have the ZS, and then we want to see that if this ZS, how much does this ZS changes when we connect the transmission line, that you have to rotate the counterclockwise. Okay? So this is towards the load, and this is towards generator. If we have a point like this, for example, okay, and then if we want to see that what is the amplitude and phase of this, because here you cannot see that what's the amplitude and phase of this. So the phase you can simply just connect and then see that here what's the value for the phase. For example, it is mentioned this is 40 degree, this is 35 degrees. So
We can't see anything, sorry.
Thank you.
I want to see that what is the phase of this point. Okay, the phase of this point, you just draw a line and you see that the value of the phase, for example, here is 40 degree, here is 35 degree, so for example here is 37, 37.5, something like that. So this is the phase of your gamma. And then you calculate this length. So this length is 1. Okay? And then the fraction of the length gives you the absolute value of the gamma. For example, if this length is 5 centimeter or 10 centimeter and this is 2 centimeters only, then it is 2 over 5 multiplied by 1. So this is the absolute value of the gamma. So this range is giving you the gamma naught absolute value, and this phase gives you the absolute value of the phase of the gamma. Yes. You have question? What do you mean?
Inside circle is angle of transmission. Gamma is angle of reflection.
Yes, you are right, actually. Excuse me, this is, yes, you are right, I made a mistake. Here is the, yeah, this is 70, for example, this is 70 and this is 80. So the angle, actually this angle is not 35 degrees. So this angle is, I don't know, 70 something. Yes, thank you very much.
So why are we making the second circle?
Because this angle is not 35 degrees. This angle is definitely more than 35 degrees. I mean, when you find the angle here. Okay.
Okay, and
All right. So actually what I said is here in 6 steps, that if you find the input impedance of a transmission line which is terminated with ZL, the first of all you need to do the normalization of the ZL. So you normalize the ZL and find the ZL with lowercase. Okay? And then we locate this ZL on the Smith chart. You know that how you can locate. I told you that this ZL is ZL equals to RL plus JXL. So you know that what's the value for this RL and what's the value for JXL, and then you find the intersection of the constant RL circle and constant XL circle, and this is the point for ZL. And then you can see that what's the value for gamma naught. At that point you can, I just showed you that how to calculate the amplitude and how to calculate the phase of the gamma naught. And then you are moving around the ZL by twice of this beta D, which you calculate based on the lambda. For example, you calculate that beta D, 2 beta D is, I don't know, 100 degrees, based on the beta, which is equals to 2 pi over lambda, and this lambda is the lambda of the transmission line. It could be, for example, lambda naught divided by a square root of epsilon r. And then you know that the D, I don't know, they said that the D is, I don't know, a value, any value, a quarter wavelength or half wavelength or anything. And then you find the new point. And then at that new point, you can just directly look at what's the value for the Z in at that point, and then find the Z in, but again, the denormalizing of the value that you read on this image. Clear. In this example, we say that the impedance of 30 plus J60, I want to connect it to a transmission line with the length of 2 centimeters, and I want to see that what's the new input impedance. So we have a load connected to a transmission line. This transmission line is 2 centimeters and it is 50 ohm, and this ZL equals to this value, and I want to see that what is the Z in, and frequency is 2 gigahertz. F L Z naught. Okay, I want to see that what's the value for Z. First of all, you normalize the ZL. We have ZL divided by Z naught, the impedance given, Z naught is given, so this is the value. You have to find the point 0.6 as the real value. The intersection of the R equals to 0.6, and the intersection of these two graphs, X equal to 1.2. Can you find that on your Smith chart? R equals 0.6, and then X equal to 1.2. It should be somewhere here. Okay? Yeah.
We'll take the values of
Just louder.
we'll take the value of 0.6 and 1.2, the red ones or the blue ones.
Red. Only red. Forget about the blue. Just red. Blue is admittance. We will reach there. So we have a R equals to R equal to 0.6. You can see the values of R here. For example, this is R is 1.4. This is R 1.6. This is R1. So R equals to 0.6 is this circle. Okay? Clear? So this is R.6. And then X equal to 1.2. Again, you can see at this. So this is X2. This is X 1.8, 1.6, and this is X 1.2. And then the intersection of these two is this one. So this is the ZL. No, both of them are positive. It's 30 plus J60. The upper plane, the upper half is positive. The lower half is negative. This is what we had here. So the upper half is positive numbers, and then the lower half is negative numbers. Okay. So you can see here that this part is positive and this part is negative. Okay? And then we need to find the 2 beta D. And then this beta D again you can calculate from 2 multiplies by 2 pi over lambda, and this lambda is C over F, so it is 2 pi 2 pi F over C multiplied by this D in radian, and then you change it to degrees. Okay? And it is 192 degrees. And then we need to move around this point by 192 degrees and then find the same point with the same radius. So if I go here, we see that, for example, here at this point, it is 71.56, and then I want to move 192 degrees. So then we have to 120 degrees also go into the lower half, and then we reach this point, draw this line and see that what's the value for this. Exactly the value should be for this. And then this is the Z. Is it clear or not? If not, I can again the rotation. So
71.
yeah, and then you have to
And we have to rotate 190.
92. So you have to go 71 up to here. So 71 up to here, and then another 120 degrees here. Okay. Of course. So the length of the line, I mean, the length of the line dependent on the frequency shows different electrical lengths. For example, a 2 centimeter transmission line at 5 gigahertz has one electrical length. Electrical length is in degree or radian. And at, for example, 1 gigahertz has another value. For this epsilon r has one value, for another epsilon r has another value. Depends on the phase velocity and frequency. The same phase. Always the same phase. Electrical length. We call it electrical length, and its phase.
What I mean is like if you keep increasing the frequency, you will reach eventually the same phase. Or is it that you increase it?
No. You see, we say that we have the transmission line with the length of 2 centimeters. Okay? With 2 centimeters, for different frequencies, you reach different phases. But if I say that I have a transmission line with the length of, for example, lambda by 8, then for different frequencies, I reach the same phases. Because this lambda by 8, I already mentioned the frequency inside that. Okay? If I'm talking about a portion of the wavelengths, of course you reaches the same at different frequencies. But if I'm talking about the actual length of the line, 5 centimeter, 2 millimeter, 1 meter, it's different for different frequencies. Okay, guys. Yeah. Loud. Sorry. So why it is 96 degree? Because you have to calculate this, that we have, guys, please, your friend asked a question, maybe this is your question. He said that y beta d equal to 96 degrees. So beta d we have to calculate from this formula, and it is 2 multiplied by 2 pi, and f is 2 gigahertz divided by 3 10 to the power 8 multiplied by 2 centimeter, which is 2 10 to the power minus 1. We can calculate this and then change it to degree. So this is in radian. Sorry?
Shouldn't it be minus 2 because it's in centimeter? So if we take it in meters, it's going to tend to be
Minus 2.
If this whole thing comes minus
Yes. All these. No, this is 192. This is 2 beta d. Okay? So we have to move on. We have lots of things to say. All right. So the next part. Okay, guys.
Would the distance change?
We will reach to a Smith chart later when I want to solve few questions for you, okay? So the next thing that if I want to make what we see from previous lecture, that if we put an open circuit transmission line, so if I put an open circuit open circuit transmission line, I might get hacked. And then the input impedance of this open circuit transmission line, which is with the length of L, I said that this Z equals to J minus J cotan of beta L. It means that with the open circuit transmission line, I can make a capacitor or I can make an inductor dependent on the length of this transmission line. Okay? This is what I wanted to say. I can say that the impedance of a capacitor, we can say, is like this, the impedance of a capacitor, and the impedance of a transmission line with the length of D1 is this value. Then the relation between this transmission line and the value that if I can just replace it with a capacitor is coming from this formula. Exactly for the inductor, I mean a piece of a segment of a transmission line can be represented as an inductor, and then the value for the inductor, the input impedance of an inductor, is coming from this formula, J omega L, and normalize it, and then it comes again from this formula, and then this is the, I think I forgot Z naught here. This is Z naught cotan. Okay. Again, the length of the transmission line, if I select as this number, then I can say that this transmission line acts as an inductor. For example, if we have a capacitor 2 picofarad and I want to make a transmission line that acts as a 2 picofarad capacitor with the intrinsic impedance of 50 ohm at 3 gigahertz with the phase velocity of 0.77 of C, then the length of the transmission line that I should pick is this value. Or for an inductor of 5.3 nanohenry, then the length should be this value. It means that, so the start of the transmission line is from open circuit, because it's an open circuit, and open circuit point is here. We just mentioned in the first slide that here is the open circuit, here is the short circuit, and here is the match. Okay, so we start from open circuit and then moves by this length of, for example, D2 that we calculate from these equations, and the length, if you calculate, is this value. Then we reaches to this point, and this point exactly shows that your XC, for example, is 0.53, and it is equals to 2 picofarad. The same thing for the inductor. So we start from this point, and then it says that the length should be this value. So we start from this point and then reaches to here. So XL equals to 2, and it is equals to 5.3 nanometer. The same thing we have for the short circuit transformation. I mean, again, we can say a transmission line, which is, I don't know why. A transmission line with the length of L. If I terminate it with a short circuit, then this Z in again equals to J Z naught tan of beta L. We had this in previous lecture. And again, if I equalize this with the impedance of an inductor or a capacitor, then we can find what should be the length of this transmission line to have a predefined value. The same example, and then these two numbers. You see that these two are kind of conjugate of each other. I mean, the value that they generate are conjugate, because for a short circuit transmission line, if you use this length, you will find this value of L. And if you use the same length, you will find this value of capacity for the open circuit, and vice versa. Okay? Now we are reaching to the blue section. So what you have on your graph as a blue. Assume that we find the Z in. Okay, how I can find that, what's the value for the admittance on this chart? Because I need this. In most of the impedance transformation, you have a combination of components in series and in parallel. So sometimes we need the impedance, sometimes we need admittance. So if we assume that we have this Z in and the value is coming from this formula, then we can say that Y in is coming from this formula, and this formula is exactly, again, 1 plus e to the power minus jp, 1 minus e to the power minus jp gamma d. Okay? So this is changing to this. If I want to find the value for Y in instead of Z. So what does it mean? It means that I can simply rotate the value for Z in by 180 degree and then look at the Smith chart and see that what's the value for Y. Any value of the gamma d, if I rotate it by pi, then instead of Z in, it gives you Y. Just rotate and then look at what's the value here at this point. This point is the intersection of which two circuits. And then that's the Y. Or, which is more convenient and more useful, instead of rotating this Z in, I'm rotating the Smith chart 180 degree. Okay? So it's simpler. Because if I have a Smith chart, I mean, this is more convenient, that if I have a Smith chart that it has the Z and it has the Y, and the Y is only 180 degree phase shift of the Z, then you don't need to rotate the point. You just look at the point, it shows both of them, the Z in and Y in. Now I have two Smith charts on one graph. One of them is Z Smith chart, one of them is Y Smith chart. And the Y Smith chart is exactly the 180 degrees phase shift of the Z Smith chart. Okay? So instead of rotating the point, I just rotate another Smith chart and put it there.
Can you show it on the...
Yes. So here, is the Z in equals to infinity. And then I can say that here is Y in equals to 0. Here is Z in equals to 0 and Y in equals to infinity. This point. Okay? I mean that if this is the center point of this is the original point of a Z Smith chart, This is the original point of a y Smith chart.
For the point that we have in the previous example.
Yes, in this previous example, you had this, I will show you. You have this ZL equals to a value, okay? And you read this from these red circles, okay? Now you just read it from the Y circles and see that what's the value. This is the Y. So this is the YL. So from the Y, I can say that, okay, this is somewhere here. So this is 0.2. I have 0.2 here and 0.4 here. So this value is somewhere between these two. It's, I don't know, 0.33. Okay? So the YL equals to 0.33. And then the J, I mean the B part of this. So again, I have here 0.7 and I have here 0.9. So this is between these two. And this is minus J 0.8. Something between these. Clear? No? No. Okay. Assume that we have this point, okay? What's the ZL for this point? So ZL equals to, I read the intersection of these two circles. So this is one circle, okay? And this is another circle. This is the real one, this is the imaginary one. Clear? So this real one is 0.6. So the value for ZL is 0.6 plus, and this imaginary part is 1. You can see here 1. Clear? So this is J1. So this is the impedance. All right? And if I want to see that what's the admittance of this, again, this point is the intersection of 2 points on the y plane, two circles on the y plane. This circle, one of them is this circle, and this circle. Okay? So this circle is coming from, for example, somewhere between 0.4 and 0.6, which is 0.5. And this circle is coming something between 0.7 and for example, 8. I don't know, 0.72, J 0.72. Is it clear now?
Those lines are not very
Clear, but the numbers are clear in the outer. You should just look at the numbers. So the blue numbers in the outer part of the circle is clear, I think. And the numbers is important because you can draw the line by yourself. So what I can tell you, just consider that. Please consider this, that in the Z plane, here is the plus J, here is the minus J X, and in the Y plane, here is the minus JB, here is the plus JB. Because I rotate that 180 degree, you can see that the top half is coming to the bottom and the bottom half is coming to the top. Okay? Clear? Alex, clear? Is it clear? Yes? And this is what I just mentioned, that we can have both of the Smith chart, the Y Smith chart and S Smith chart on the same plane. So we said that we have a Z 0.5 and plus J 0.5. So this is the Z equals to, actually Z equals to RL ZL equals to RL plus J XL. So RL equals to 0.5 and XL is also equals to 0.5. And then we have the YL equals to GL plus JBL. And then we see that from the Smith chart that this GL is 1 and this BL is 2 at this point.
For admittance, capacitance is negative, right?
Oh, sorry, 1 minus 1. No, minus 1. This is something else. This is point B. It's another one.
How is it minus 1?
Because 1 divided by 0.5 plus J 0.5 equals to 1 minus J1. You can calculate it by your calculator.
But admittance equals to 1 over impedance.
This is what it should be.
For admittance, capacitance value is negative, right? Just opposite of.
Opposite of that, yes. We will see we will reach to the capacitance and inductance representation. Clear? And then for the point B, which is 1 plus J2, then you see that the ZL is, for example, 0.4 plus J 0.4, 0.2 plus J 0.4. Is it clear? Okay, guys. Please consider that you will have one question on the Smith chart. So try to learn this. Okay, don't skip it.
B is another example, right?
This is another. We have 2 points
We are finding the impedance now.
for B. Yes, we have the admittance. You can point the admittance and then look at, without moving to anywhere, you can just look at the what's the value for the impedance. Yeah.
We can directly put the admittance from the picture. Yes, you can
Directly. When we have this point, you can see that what's the value for the impedance of this by intersection of the R and X, and see that what's the value for admittance of this by the intersection of G and B. Easy. Okay, guys, now we have few basic circuits. RL in parallel. So what is RL in parallel? The representation of this on the Smith chart. The RL in parallel, we have, I think I have to change this to, okay. So what we have here is that as they are in parallel, so we are interested in admittance. Okay? So the admittance of a value of R is coming from this formula. The admittance of a L is coming from this formula, and then these two in parallel is coming from here. So you see that it will have a positive conductance and susceptance, negative susceptance. Okay? As it is negative susceptance, it's coming in this region. And you see that for different frequencies, it can have different values. For example, if the R is equal to 1, then J equal to 1. I mean, if R equal to 50 ohm, then J equal to 1. And then it's on this circle. Okay? For 500 megahertz, the value of the J omega L, I mean this one, is minus J 1.59. And at 4 gigahertz, the value is minus J 0.20. But it is always in the upper half. I mean, independent of what is the frequency, it is always in the upper half.
It's also written in the scripture that the upper half shows the conductor reactance.
Because the upper half is the negative susceptance. If I write down correct.
Negative susceptance for admittance.
Upper half is negative susceptance, lower half is positive. But for the impedance, so the upper half is the positive reactance and the lower half is negative reactance. Okay. So here we have a series connection of the R and L. Again, we have the normalized R from this formula, normalized L from this formula, and then the series of these two are coming from here. We have a positive resistance and positive reactance. Again, it's in the upper half because this is following the Z Smith chart. Okay, so here is, it is here, and here we have a positive reactance. What's up?
And lower negative reactance, right?
From up a bit.
So upper half is positive reactance, lower is negative.
Yes, and lower, I don't know what it happened. Okay, maybe it's time to break. It needs break. So as today's lecture is a bit long, can we continue on 4:35? Sorry for that, but we have to wrap up this because you need this in the next lab. Yes. All right.
What do you mean by admittance, impedance, susceptance, reactance? How do you distinguish?
Okay, impedance.
Impedance is resistance.
No, impedance is R plus JX. So this is impedance. This is
How do
resistance.
you define impedance?
Impedance has a real part and imaginary part. So, okay. So,
Multiple terms like so. How do you say so capacitors impedance is susceptance?
capacitors is just a reactance.
Okay.
So, yes, and this is reactance. Okay. And then we have Y equals to G plus JB. And then we call this the conductance, sorry, we call this the admittance. admittance. We call this conductance. And we call this susceptance.
I understood the equation. How do you define each term? Like, what is, how do you?
The relation is this: z is 1 over y. I mean, is equal to, if we have z equals to r plus j x, then this is equals to 1 over g plus jb. This is like this. How we can say R in series shows resistance, R in parallel shows shows conductance. For example, L in series shows reactance. Okay. L in parallel shows susceptance in parallel. C in series shows susceptance. C in parallel shows reactance. So this is, if I say that this is res, this is conductance, this is reactance, this is susceptance, this is susceptance, this is reactance. Now clear.
This is inductor.
This is inductor and it shows reactance.
So when we say that an inductor has so much reactance, what do we mean? What do you mean by that reactance?
So reactance means G omega L. It is in ohm. It is calculated in ohm. It is exactly similar to R, but it's imaginary. I mean, it does not consume power, but it shows that value of impedance.
For susceptance, it is
The susceptance is exactly similar to conductance. So it is the unit is Siemens, 1 over R. Similar to conductance. It's 1 over ohm. Yep.
Here we get the point degree 71.56. Then
Yeah.
we need to rotate it 192.
Yep.
So
So 71 here, another 120 here.
how do we find? So 192 minus 71. So
No,
that we can get
yes, 120.
120. So if we add this one 0.25, this one 71.5, and this 1.25.
No, this is 0. Here is 0.
There is 0.
Here is 0. Here is this degree. So 2010, this is 0 degree.
Oh, so 192 minus 79.56, we get 120.
120 and
From
then
0 to 120,
from 0 to 120.
this one. Okay. And for inductance, upper half is minus susceptance, lower half is minus positive susceptance.
Yes, but for inductor, in susceptance or inductor, it's always negative. I mean, always it's here because of this formula, because this L is positive.
Always
The
in the
value of
upper
L is positive. The value of Y naught is positive. The value of omega is positive. So this is always negative.
So always
And it
negative
is
on the upper part.
always
So there is no positive susceptance for
inductor. It is for
for
capacitor.
for impedance, upper is positive reactance, near is negative, lower is negative reactance.
Again, we have only positive because this value is always positive.
Oh, so there is no.
So for inductor, it happens. I mean, it is always in the upper half.
If the load is like ZL is equals to 0.8 minus J 1.2, for
Okay.
example, then 0.8 is
0.8 is here, this
here.
side, this
This
side.
is 0.8.
No, this side. So these are more than 1, these are less than 1. For Z. For Z, these are less than 1. For example,
0.8 is here,
Yeah.
and for minus 1.2 we go this way.
and then minus
Minus 1.2
1.2 is here, so it is the
This is our ZL.
Yes.
So you can find also YL here by
Yes.
looking at this.
By looking at these circles and these circles.
And total Smith chart is 0.5, right?
Lambda by 2.
Lambda by 2.
Yeah, the whole. Because we had from previous lecture that if we have a load and we had a transmission line with lambda by 2, again we have the same load. And it shows the same input impedance as your load. Okay?
Just the calculation that we had for the angle, I think it's the entire thing is 96 degrees rather, because beta is 2 pi by lambda
Yeah.
and pi times frequency is 2 gig and 3 times the power 8. And if we just multiply it by 100 for the distance, so this is what we get. And if we multiply by 2, which is 2 beta,
Can I see previous one?
so this is just beta d.
2 pi over lambda. Okay. This is this. Okay.
Beta d,
Yeah.
and then just multiplied by 2 gives us this.
Yeah.
So this is in radians, and if we convert, that's 96. So the whole angle should be 96 and not 192, isn't it?
But this is from book. So this is what they calculate as 2 beta d is 192. This is because of this. Because then, yeah. So then this is not C, this is 1 point.
1.5.
I will update this. I forgot to. So here is yeah. It's not C. It's VP. Okay, thank you very much. Question.
I'm not sure about why when the higher frequency
Because when the frequency increases, this value decreases. Because this is 2 pi f. So when the frequency increases, this susceptance decreases.
and I'm not sure what is the definition of
Susceptance is this BL. So if I write you here that susceptance, if we say that y equals to J plus JB. We call this conductance, we call this susceptance, and we call this admittance. And if we say that Z equals to R plus JX, we call this impedance, this is resistance, and this is reactance. Okay. This is our definition.
Also, how can we find the frequency in this?
So frequency actually is depends on the lambda. So you can see that what's the value for the lambda of this, I mean the beta. So the frequency is showing the electrical length of the line, something like that. I mean based on this value, so it is omega, so 2 pi f L y naught, so this is the value that you see, okay? And then based on this you can write down, instead of this C you can write down instead of this F you can write down the C over lambda, and then you can find out what's the value for this length of the transmission. I mean the electrical length.
How can I find which circle, for example, is 500 megahertz?
So not which circle, based on this value that you find for the JB. So you can see that JB is, for example, 159. Okay, so this 159 at 500 megahertz, the value for this B is 159, and then this is the 159 circle. Or at, for example, 4 gigahertz, the value is 0.2. So this is the 0.2 circle. So they moved from this point to this point if you change the frequency. Okay? No. Okay, shall we continue? Okay. Okay. So the same thing we have for the capacitance. So if we have a capacitor in parallel with a resistor, again, we can say that as it is in parallel, we are interested in admittance Smith chart, and in admittance Smith chart, then we find the value for the conductance as this value, and the susceptance as this value, and then the whole admittance is coming from here. You see that we have a conductance and a positive susceptance. So it is happening in this region. And this region is positive susceptance. Okay? And a series of a capacitance and a resistance. You see that again, as it is series, we are looking into the impedance Smith chart. And impedance Smith chart, we find the resistance as this value and reactance as this value, and we see that the reactance is negative. And reactance negative, again, we are interested in this region, and it is always in this region for any frequency. So this is negative reactance. Okay. We have one example here, and I would like you to solve this example because it's very important to understand that when we have a load, which is this is the load, we see that from lecture 1 that the input impedance of a transistor can be modeled by an R and C. You remember that a BJT transistor has in the input, it has a R pi and C pi at the input. So assume that we have a transistor and we want to match it to a 15 ohm line. We are going to this question at the end of this lecture. But if we have this transistor with this R pi, that the value is 31.25 ohm, and the C pi, which is 1.91 picofarad. If I add these three elements, a T network, LCL, a band pass filter, if I add this T network, then what would be the input impedance of this circuit? And you will see that then the input impedance of this circuit is 15. Okay? Let's do this together. So the first thing is that you have to find the input impedance or admittance actually, because here is parallel at point A. So this is point A, and then the point B, again admittance. So we need the YA and then YB, and then we have to change this YB into ZB because then it is in series with this one. And then we look at the here at ZC, and then change this ZC again to YC because it is in parallel with this capacitor. And then look at here at point YD, and then finally again change it to the impedance because it is in series with this L2, and then look at this ZE, and then we see that this ZE is 50. Please run this on your Smith charts, and I will also document camera, right display, and Okay, the first thing is that you have to find that the impedance of the, what's the value for the impedance, what's the value for the resistance of this transistor. So the resistance of the transistor is 31.25. First step is to normalize that. And we know that the transmission line, assume that our transmission line is 50 ohm. So we normalize that to 50 ohm. So we find that, and then I said that we are interested in admittance. So this Y at point A equals to the 1 over R divided by Z naught, which is equals to 1.6. What's the unit for this? 1.6 watt. Siemens. Okay?
Just one question. We are getting the admittance because it's in parallel connection.
Yes. Yeah. Okay. So where is the point 1.6 of admittance? Where is the point 1.6 on admittance? Did you find that? So when you look at these values here, so the red values show the value of the resistance, and the blue values shows the value of the conductance. Okay? And you know that this line is the pure resistive or conductive line. Okay? So the value for A is exactly at the 1.6, which is here. Okay, so here is point A. And then the next step is to add this capacitor, I mean CL. And then this CL, again, in the admittance, you have to find the value for the susceptance of this capacitor, which is coming from this formula. Actually, it is coming from this formula, 1 over J omega. Susceptance is coming from 1 over J omega C Z. Okay, which is J omega C Z. And the value is this one. So now we have to move 1.2 from this point, from point A in the positive susceptance. What is the positive susceptance? I should go up or down? Down. So what is the value for 1.2? So the value for 1.2, it is mentioned on this graph. Here, it is mentioned here, if you see. Here is 1.2. So this is the 1.2 circle. Okay, and then we have to move to the intersection of these two, which is here. So this is point B. Point B is admittance, conductance. Yes, it's conductance. It's J. It's G. Blue value. It is conductance. Yeah. Is it 1 point? Yeah, true. It's blue value. I didn't get. Yeah, it's 1.6. Is it 1.6 or 1. I thought maybe this one is 1.8 and this one is 1.6. I think so. Is it clear, guys? I just moved to this point, which is 1.6 plus J 1.2. Point B is there. All right? Now I have to look at the impedance of this because I want to make this circuit in series with one inductor. Okay? So what's the value for impedance of this? Just look at this point and read the red line. So one red line is coming from this point 3, and then this also is coming from point 4. So it is 0.4 minus J.3, which is we have here. Easy? All right. Now I'm going to add this amount of reactance to my circuit. Okay? Which comes from the value of the L, which is 1.1. So how did I find this? You have this value for the L, 4.4 nanohenry, and then you know that what's the value for the omega, which is getting here from the S. So you find this value of L. Always consider and don't forget to normalize, because if you don't normalize this, you get a, I don't know, value of 56 or something like that. So it's 55, so it's wrong. All right? So always normalize that. So we are working on normalized values. And then you add this 1.1 to the previous that we have 0.4 minus J.3 added by 1.1, we are going to 0.4 plus J.8. So we are moving to 0.4, intersection of the 0.4, which is the red 0.4, it's impedance. So this is the red 0.4, and this is the 0.8. This is 0.8. Okay. So we are coming here. Again, I'm looking at the admittance of this, which is very easy. It is intersection of this circle and this circle. So this circle is coming from this number. This circle is coming from this number. If I don't make a mistake, or this number maybe. Yeah, 0.5 and 1. So this is 1. So this is minus J1, and this circle is 0.5. Okay?
Can you repeat point C again?
Louder.
Can you repeat point C again?
C. So for C, so you understand that we have to go to this point. True? So just look at what is the value, what is the location for this point. 0.4 plus J 0.8 on the admittance. So 0.4. So 0.4 is this circle. You see that this is 0.4. Okay? This is 0.4. So this circle is 0.4. Am I on? Sorry, it's on impedance. It's on impedance. So this is 0.4. This is 0.4 circle. Okay? And also 0.8. So 0.8 is it 0.8? Yes, 0.8. You have to look at the. So this is 0.8. So this line. So the intersection of these two lines, which is this point. YC, you should read YC. So So YC is the intersection of this line and this line. This is 0.5, I think, and 1. And now I'm going to add, so this is C. And then I'm adding another capacitor. Again, you calculate the normalized value of this capacitor, which is 1.5. I add this 1.5 to this number and we reach this point. 0.5, J.5 on admittance. So 0.5 plus J.5. So it is somewhere in the lower half. So 0.5 is again this circle, and J.5 is this circle. This is J.5 and this is 0.5. So this is the point D. And then we read the value for the impedance. The value for the impedance is the intersection of this circle. This is circle 1 and this circle. And this is also circle J1. So this is minus J1 and this is R1. And then you add the value of 1 and you see that the final value equals to 1. And then we denormalize it and we see that it's 50 ohm. So by adding some capacitors and inductors, we change the input impedance of the transistor to 50 ohm. Why we are interested only with capacitors and inductors? Why didn't I add a resistor, for example? I can add a resistor and then just move from, I add a resistor and then move on this line and reach to this point. Yes, true. Because resistors consumes our power. And we never use resistor in impedance matching.
So why you finally denormalize it?
Because now I want to come out of this Smith chart and say that what's the Z in. So the Z in is the value that you see here multiplied by the characteristic impedance of the transmission line. Because in the first step you normalize in each step actually you normalize. So you normalize your values and insert it into a Smith chart and play around that. So in the final step, when you read the value, again you have to. Yes. Again, for example, a transmission line, we normalize it and say that a transmission line is just a phase shift. It just changes the phase. So normalize and then go inside this. So it is only a phase shift.
I have a question on point D.
Yep. Point D.
If my on point D, if my capacitor is in series, then it would be add to the JC, right? Not YC.
Yes. You mean that instead of this circuit we have this circuit. So everything is then in Z. So not here, you don't need to change anything. Z, another Z, another Z.
But isn't it that capacitance in series gives this acceptance?
Capacitance in series gives you susceptance, yes.
the reactance of the inductor, then again
Why
find
it's
the
not
corresponding susceptance, and then add the susceptance of the capacitor, again find the corresponding reactance and find the susceptance.
No. So capacitance gives you, in series again gives you reactance. It does not give you susceptance. It gives you a reactance, but it's a negative reactance. I mean the value that, I don't know why it's going like this, but
We only concern about the admittance and the impedance. We only concern about the admittance and the impedance.
on the Smith chart, you are looking at the impedance and admittance, and then you calculate the values for the impedance or admittance of the component that you have. If it is in series, then you have to look at the impedance. And impedance of a capacitance is just a reactance, pure reactance. Okay? But it's a negative reactance. It's a negative reactance. Okay, guys, we are going to networks, what we mentioned at the beginning. So the networks, guys, okay, leave it for after the class, okay? So the networks. It is very useful that we are looking into a circuit, I mean a complex circuit, without understanding what's going on inside that. Because when we have lots of components, for example, you have an op amp, tens of transistors, lots of parasitics inside that. But when we are looking at a black box, by just looking into the ports that we define for that black box, and then we characterize that black box, it's very useful especially in RF electronics, because it's not important that what's going on inside this network. If I know that what is the voltage, input voltage and current of this network, then I can simply connect this network to the rest of my circuit and then use it and characterize it and analyze my circuit. So it's very important to divide complex networks into sub-networks and then analyze each of them, find the parameters of those networks, and then play with the network parameters. This is the idea. So most of the time we are interested in the overall circuit performance instead of the individual components. Okay? So we define one port network when it has only one port, two-port network when it has two, and then multi-port network when it has more. All right? In electrical and electronics, so the things that we are mainly interested, especially in low frequency, is the current and voltage. Anything in the electronic we can define based on the voltage and current. So, and then we say that a port of a network has two variables, I and V, and then we characterize the specification of this network based on these two parameters. We have 4 different types of parameters. We can say that a network can characterize based on the Z parameters or Z matrix. And this Z matrix coming from here. If I say that the voltage at the port I, or at the port, for example, in 2-port network at port 1, what is the relation between the voltage at port 1 with the current at port 1 and current at port 2. And then I define two parameters, Z11 and Z12, and these two parameters is the characteristic of my network. And again, for V2, we have another two parameters. Clear? So we define the ZNM in an N-port network, the Vn divided by In when the other currents are 0. So here, if I put I2 equal to 0, then the Z1 equals to V1 or I1. So this is how we calculate the values for the Z. So I just open circuit the port 2. No current is going inside that. I measure the voltage at port 1. And then I said that Z, okay, Z, for example, 1 is this value. Again, I open circuit the port 1, and then measure the V1. And then I said that Z12 is this. Okay? The same thing we have for the admittance networks, admittance, or Y matrix. So we say that the admittance parameters is the In divided by Vm when the other V equals to 0. I mean when the other ports get short circuit. Okay? So I short circuit port 2, so then V2 is equal to 0, and then measure the current at the port 1. And then I said that, okay, Y11 is this value. Is it clear? And we have these different representations because they are useful in different situations. We will see this. In different situations, for example, in one situation, the Z matrix is more comfortable, or ABCD matrix, or H matrix, or Y matrix. And then we define based on this. I mean, for a two-port network, I say that the voltage at port 1, how it depends on the parameters at port 2. Or the current at port 1, how it relates to the voltage and current at port 2. Okay? So ABCD matrix we define like this. And for the H matrix, actually we define the voltage 1 based on the current 1 and voltage 2. And the current 2 based on the current 1 and voltage 2. This is mainly used in the characterization of the transistors, low frequency model of the transistor, because you remember that in low frequency we say that how we see that what is the HFE, and then what's the H1. So these are what you learned from the analog electronic. Because output, for example, output voltage, it is dependent on the input current. So this is the relation that we had. So an example of the networks. Assume that we have this pi network. So this is a pi network. 1ZA, ZB, ZC. And I want to characterize this, and I don't want to consider that what's going on inside this. I just find the value for Z11, Z12, 21, and 22, and then we will have these values based on the definition. And then I have a Z matrix, which is equal to these 4 parameters. Okay? And then I can say that, okay, I don't know what's inside this, but it has a Z matrix with these values. For example, ZA in parallel with ZB plus ZC, or the rest. And this is what I just mentioned, that, for example, a common emitter, a small signal model of a BJT transistor, we can draw a small signal model based on this, and then we can define the H parameters of that. That what's the relation between the VBE and IB, which is the input impedance. What's the relation between VBE by VCE, which is the gain, or GM, I mean the gain, actually, the gain of the transistor, and then what is the voltage gain, and then what is the relation between the IC and IB, which is the current gain, and then what's the relation between IC and VCE, which is the output impedance. I mean, inverse of output impedance and inverse of, this is the inverse of the forward gain, this is the inverse of output impedance. Okay? I don't know why it's like this. We have it. Is it? Okay. So I said that in which situations, which of them is more convenient. For example, if I want to put two networks in parallel, then Z parameters is more convenient. Okay? So I have the Z parameters for network 1 and Z parameters for network 2, and then the Z parameters of the total is Z1 plus Z2. Okay? When I want to make two networks in series, this is in series.
So H11 means H11 means
No, Z. We are
you put earlier that H11.
here. It's gone. So H11 was the input impedance of the H matrix of a network. H. 1 means for port 1. It's a definition. We say H11 and this H11, I don't know. If you have your, I don't know why it's like this. Maybe, okay, I think the main problem is that this system is full. H11 is a definition here. So we said that H11 is the relation between the V1 and I1 if V2 is 0. I mean, if I short circuit the output, then what's the relation between the input voltage and current? And I call it as input impedance of a transistor. Okay? Again, if we put the networks in series, but with this, I mean series of the inputs and parallels of the output, okay, then H parameters is useful. So H of total is H1 plus H2, or H prime plus H double prime. Okay? If we put the two networks in parallel and I want to find the network parameters, then the Y parameters is important. And then we can say that the Y1 plus Y2 shows the Y of total. This is why we go for the different representation of a network. And if we put two networks in cascade, so I have network 1, and this is very common in Electron. For example, you have a network 1 and another network, and you want to connect these two together. So what will be the parameters for the whole? Then this is ABCD1 multiplied by ABCD2. Okay? So ABCD parameters is very useful in electronics. Most of the scientific papers, if you look, if they have different components and they want to show that what's the whole performance of the circuit, they use ABCD matrix. And then here we have the ABCD parameters for simple components. For example, for a single transmission line with the impedance of Z, then the ABCD matrix is this value. For a transmission line in parallel, then the ABCD matrix is this number, these numbers, and then for the T network, for a pi network, for a transmission line with the length of L, and then for a transformer. So these are the ABCD values for the ABCD.
How are we going to use this matrix?
You have this circuit, and then you have a transmission line, and you want to see that what is the whole thing. So you find the ABCD of the first one, you find the ABCD of the second one, and then multiply together and say that, okay, the cascade of these two has this ABCD matrix. Okay? And then all these parameters can convert to each other. For example, if you have the Z matrix, you can find the ABCD matrix. Or you have the Y matrix, you can find the H matrix.
All are 2 by 2 matrix.
All for two-port networks. We are talking about only two-port networks, because multi-port networks, we have only Z and Y. We don't have A, B, C, D, or H. Okay? This is an example. Okay? This is an example. We have matrix 1. We have network 1. So this is the network. This is our matching network. I have one transistor. This is the second network. The output matching network, third network, and then the feedback, which is the fourth network. So if I want to calculate what is the value for the whole network, I calculate Y. First, I calculate the H matrix for this. Then I convert the H to Y. So first, the H of the transistor, then I convert it to Y of the transistor. And then I add this Y to the Y of the resistor. Okay? And then I change all these two as the ABCD. Change it again to the ABCD of the combination of the transistor and resistor. Okay? So this is the ABCD of this part. And then I multiply the ABCD of the input network, multiply by this, and then multiply by ABCD of the last one. This is how it works. This is why the networks are important, because maybe analyzing all these together is difficult, but analyzing every part and then connect them together is much easier, especially in the computer programs, because in computer programs, in the conversion of the matrices, these things are very easy, and you can do that there. Okay? In high frequency, but these are mainly for low frequency. In high frequency, we are defining something else, and this is S parameters. So networks are mainly represented by their S parameters. And S parameter is actually coming from the idea of the power. I mean that how much power we send to the one port, and then how much power we receive at the other ports or the same port. I mean, this is coming based on the power, because in the high frequency, we are always interested in power. How much power we generate, how much power we can transfer, how much power is reflected back, how much power is lost inside the network. So these are the things that we are interested in. It's a matter of power, mainly. So I believe we are defining two new parameters, AN and BN. And then I said that this AN equal to this equation. And you remember that from previous lecture that if we want to calculate the power of this Pn, the power of Pn, which is related on the voltage of network, voltage of 1 and current of 1, then this is the formula. And this formula is then simplified into this value or this value. And then we call this the power that we sending to the port 1, and this value is the power that reflecting back. So the average power as at any port is the power that we are sending and the power that reflected back. So based on the definition of this Vn and In and this An and Bn. And because of that we said that we are interested in power, because you see that this An and Bn are in the form of power, mainly are in the form of power instead of voltage and current. And here we say that based on the formulas for Vn, that you know that Vn equals to Vn plus Vn minus the forward voltage and backward voltage, and In again equals to In plus In minus. Then if you replace these two, we find that An equals to this one, which is forward, and this one, which is backward. Clear? And then we define the S parameters as these values. I mean the reflected power, for example, we define the S11 as the reflected power divided by the incident power. I mean how much power I send to the port 1, then how much power I received at port 1 when there is no power at port 2. What does it mean when there is no power at port 2? Because for the Z parameters, for example, I said that when there is no voltage. And for the Y parameter, I said that when, for the Z parameter, I said that there is no current. Or for Y parameter, I said there is no voltage. When I said that there is no power, what does it mean? Okay, I mean that what's the condition for no power? No power at port, I mean no power coming to port 2. Open circuit. Short circuit. Short circuit. Match. Not mismatch, match. Yes, I mean no power is coming from port 2. If you match the port 2, nothing is coming back. So we have a two network, okay? I transmit a power A1 and then I measure something which comes back, okay? If I want to make sure that nothing is coming from this port, I just need to match this. Okay? So for the Z network, we open the port 2 because we said that no current is coming. For the Y network, we short circuit because we said that no voltage should be at port 2. And then we calculate the, for example, Y parameters of the port 1. For the S parameters, we match. I mean, we want to make sure that there is no power coming from the other port. So this is port 1, and this is port 2. And then we define, for example, S21, how much power we receive at port 2 when we transmit something at port 1. And then we say that when the again the A2 equals to 0, I mean no power is coming here. We will match here, and then we measure what is coming here.
What do we mean by no power is coming?
I mean nothing generated from port 2 into the network. When nothing is, when from these 2 points, nothing is going into the network. When we want something like that, it means that we have to match it. Because anything which comes out of this network, or anything which comes, for example, from the space, if you match here, it damps into this Z naught.
No power means no reflection.
No, no power. No power. It could be a reflection, or it could be something which comes from somewhere else. I mean, it could come from your network.
Not being fed back into the network.
Yes.
The
It
power
could be. The source could be internal or external.
S21 means power is on the port 2, but not power in port 1.
S21 means the power which is received at port 2 and transmit from port 1. S11 means the power which is received at port 1 and transmit at port 1. How many power I transmit into port 1 and then I got it back. So it's a kind of, the meaning is the reflection, which I mentioned here. Okay. The same thing for the other port. How much power I received at port 1 when I transmit something at port 2. And the same thing for the S22, which is again the definition for the reflection coefficient at the output. So based on these two, we see that the B1 divided by I1 is V minus V1 minus plus divided by V plus minus. So if you look at these two equations, so A1 is V1 plus divided by square root of Z naught, and B1 is V minus divided by square root of Z naught. Okay? So the A1, B1 divided by A1 is this value, and you know from previous lecture that this is gamma in, and this is gamma out. Okay? So these two parameters are actually has a kind of tangible meaning for you. S11 and S22 are the reflection coefficients at the port 1 and port 2. And then you remember from the previous lecture that this is the formulas that we have for the power, and then we can say that the power that we received at port 1 is this value, and the power that we received at port 2 when we transmit at port 2 is this value. Okay? You remember the equations and the definitions for the return loss and insertion loss. We had this last lecture, and then we see these two new definitions based on the S11 and S21. So the insertion loss is the how much power that we transmit from port 1 and we received at port 2. I mean how much power that we cannot receive. 1 minus that. And insertion loss is how much power that we transmit and it reflected back. So the way that we measure the S parameters, we are using VNA, Vector Network Analyzers, to measure the S parameters. So we have a transmitter and we call it RF, okay? So we are transmitting a signal from here, and I want to measure the S parameters of this device, which is DUT, device under test, okay? So I want to measure the S parameters of this. And then this device under test, for example, you bias it, we use this bias, we will see this later, that what are these bias T. And then we use two directional couplers. So directional couplers actually for devices that separate the incidence and the forward and backward wave. So they have two ports. When you send signal, then it directs some part of that to this port. When you send signal from this side, then it directs it to this port. Okay. So nothing, when you send signal, it does not go into this port. Some of them is going forward and some of them is coupled into the forward coupling port. And the same for what's this? For backward wave. Okay? So we send the RF signal. So some part of that we get at port R as a reference. I want to see that how much power I send. This is the incident power. This is R actually shows the A1. And then how much power reflected back from the device is going into the port 2. So the A is showing the B1. And then the signal is going through the device and then go through the other directional coupler. So some part of that I capture at port B, and then this port B is the B2. All right? And then the rest is going and damp into here. So this is how I said that we matched the port. I mean, nothing is coming back. Okay? And then the S11 is this A divided by the reference that we got, and then the S21 is this B divided by the reference. This is how we measure the S11 and S21. And then if we want to measure the S12 and S22, then you need to just do this way around. I mean, rotate this, turn around this device under test, and then do this again. But the current network analyzers has already two ports, and then you can do it at the same time. I mean, you don't need to turn around the device under test. It will do it for you. There are 2 ports or more than that for example, 4-port networks, for 8-port networks. We have very high performance VNA these days. Okay? Okay. Okay, we go for the quiz because this is, I think, I will continue this one next session. We can go for quiz. Okay, about the quiz. So some of your friends complained that it seems that there are some ghosts in the class. And, yes. And then send some text to their friends out of the class, and then they participate. And then they participate. So actually it's not unfair and it's not ethical, okay? So because this is the bonus for those who are coming to class. So, okay, following the ethics is one thing that you should learn in university. This is honestly, this is more important than what you learn about the Smith chart. Okay. So. please log in into the Mars with this code. So we have a load, and this load has an impedance of infinity, so it's open circuit, and then we have a transmission line with the length of L. So what's the point of this circuit? I mean, what's the representation of this circuit on the Smith chart? What's the Z in? Everybody answer? Okay. So we have a an input impedance. I mean, we have an impedance of infinity. Okay, where is the point for the Z in for here? Is A. So here is the Z in at this point. But then we have a transmission line, and we said that this transmission line is rotating this point around the circle by 2 beta D, okay, or 2 beta L actually, okay. So then the new Z in is the ZL, I mean the new, actually the new gamma in. So the new gamma in equals to gamma naught e to the power minus j 2 beta d, and this gamma naught was 1. So any point on this circle it could take based on the value of L. Okay? Yeah. So we go for question 2. All right. So we have ZL at point A, and then with one of these components we move to point B. So what will be that component? Everybody answered? Okay.
Yes.
All right. So, first of all, we are moving on the red circles, and these red circles is impedance. Okay, so everything is in series. All right, so it could be B or D, and we see that the value that we get for the J, I mean the reactance that we have, is decreasing. So the reactance that we have here, for example, is J1, J alpha 1, and here is J alpha 2, J alpha 2, and then this alpha 2 is smaller than alpha 1. Okay, it means that it has this component has a negative reactance, and negative reactance is for capacitor. Okay, so B is the correct one. And then okay, everybody answered? No. No? Okay, I think everybody answered. So a good combination of answers. All right. So what we just mentioned that, okay, it's better that I explain on the lecture slide. So what I just mentioned here is that, all right, the S11 and S22 shows the amount of power that we send at the port 1 or port 2, and then we receive at port 1 and port 2. And then I said that the return loss is this value, and then the insertion loss is this value. So the amount of power that you transmit at port 1, so this is the two-port network, and you received at port 1 is coming from this formula. And then the amount of power that we are transmitting to the other side is actually the power that we generated minus this one. Okay? Which comes from the S21. Okay? Does it make sense? If you go to the definition of the insertion loss and return loss, I mentioned last week that the return loss in linear actually plus insertion loss in linear plus the loss of the system, this divided by, the normalized by the power is always equal to 1.
Or is it related to the PSWR? So the S is the relation of
Sorry? No. Your question, no. SWR is something else. S parameters and SWR. SWR is the reflection, is based on the reflection coefficient. S11 and S21 are power.
But this is the power reflection.
Power reflection is S11 squared. Yes, true. Here we have.
So our target is always to PSWR value is equal to 1. So in future, so like the PSWR value in various scenarios is always 1.
So PSWR value 1 means that you don't have any S11 and S21 is equal to 1. S11 is 0, S21 is 1. All the power from port 1 transfer to port 2. This is what we have. Based on this formula, the power that we generate and we receive is this value. The power that we transmit is 1 V1 plus squared divided by Z naught. So this is the power that we are receiving at port 2 in this case. When we are transmitting power at port 1, how much power we are receiving at port 2 is this one. No, this is not correct. No, this is not correct. This is different. So I leave you one exercise. You find this equation that S11 squared plus S21 squared equals to 1. Find it from these, write down the power formulas, and then insert the A and B based on those, insert the S11 and S21, and then see that why this is equal to 1. And assume that there is no loss in the network. Okay? You can prove it based on this formula. A, S is the ratio of loop. See, we cannot say A is voltage or current. A is V, I mean, it is V divided by a square root of Z, not Z. And it's I multiplied by a square root of Z. Okay? So A and B are not voltage or current or power itself. Okay? It is something between. It is in the material of the power, but a square of that is power. Because this is our definition actually. We say that this is power wave. This is power wave, but not that power. Because that power is this. This power, I mean the something with the material of power is coming from A n squared or B n squared. And everybody left, but the class didn't finish. Okay, we can continue later. Yes, next week you have AES. No, it's a mixer. It's amplifier and impedance matching.